With each fascinating picture captured by the James Webb Space Telescope, it keeps on garnering thought from various corners of the universe, including planets within our own planetary system. A year earlier, we considered our most significant brief glimpse at pictures showing the Carina Cloud, Stephan's Quintet, and, strikingly, the hypnotizing Deep Field image. This explicit picture clearly depicts different galaxies resting in the vast expanse of the universe, fulfilling the assumptions made. The James Webb Space Telescope hasn't stopped being amazing. It has actually uncovered objects that challenge well-established cosmological theories. These astounding revelations are now being classified as universe breakers by cosmologists, perplexing established researchers with their ability to challenge existing ideas. The reasons for these discoveries remain shrouded in mystery, throwing our theories and hypotheses into disarray. So, what's the latest scoop from the James Webb Telescope? What remarkable new discoveries has it uncovered that were previously unknown to us? Join us as we delve into the revelations of how the James Webb Telescope has presented evidence suggesting the existence of another universe, challenging the standard understanding of the Big Bang. Our universe, as we've long understood, arose from a hotter, denser state via a theory known as the hot Big Bang. This concept, a major scientific achievement over the last century, gained overwhelming support in the 1960s with the discovery of the cosmic microwave background, CMB, a leftover from the early hot and dense state. Over time, the Big Bang has remained the dominant theory explaining the origins of our universe. Nevertheless, new and critical observations have driven cosmologists and astrophysicists to reconsider both the ongoing expansion and the Big Bang itself. Despite these challenges, alternative theories have failed to gain traction, with the enduring nature of the theory of the universe's origin persisting. According to the prevailing view, the universe's origin involves a smaller, denser universe in the distant past. The presence of radiation, like photons, indicates that the universe was hotter at its origin and has since cooled. Extrapolating backward in time, the density, temperature, and energy levels reach a point where a singularity could form, and conventional laws of physics break down, around 10^3 seconds after the beginning. In such a brief span of time, tiny distances, short time scales, and high energy levels challenge our comprehension. Rewinding the cosmic clock to the theoretical zero point, if the universe started as hot and dense, it would have expanded and cooled, producing vast numbers of particles and antiparticles. Excess particles were annihilated by radiation as temperatures decreased. The breakdown of the electroweak and Higgs balances led to the formation of the four fundamental forces and particles with non-zero masses. As the universe cooled further, protons and neutrons formed composite particles called quarks and gluons. The combination of protons and neutrons led to the formation of light nuclei, such as deuterium, helium-3, helium-4, and lithium-7. Overdense regions went through expansion due to radiation pressure, followed by gravitational collapse, leading to the formation of large-scale structures. Around 380,000 years after the Big Bang, the universe cooled enough for stable neutral atoms to form, marking a critical step where photons decoupled and their wavelengths stretched as the universe expanded. The discovery of the cosmic microwave background decades ago solidified the Big Bang theory as the most supported explanation for the universe's creation. The Big Bang versus steady-state theory debate ensued. While most cosmologists and astrophysicists embraced the Big Bang theory, staunch defenders of the steady-state theory, such as Fred Hoyle, continued to support increasingly improbable ideas, only to face defeat in the face of overwhelming evidence. The evidence presented was definitive. It wasn't fading starlight or reflected heat from dust. The astronomical glow showed an astonishing consistency, resembling an ideal black body, yet had no association with known objects in the universe. Despite this, Hoyle and his followers continued to undermine scientific progress by supporting scientifically unfounded ideas. Meanwhile, the fields of space science and cosmology underwent massive advancements from the 1960s through the 2000s, with cosmology making particularly remarkable strides. We mapped the universe, described its large-scale structure, and explored the formation, evolution, and dynamic interactions of galaxies and their stellar populations. Still, even with these advances, we encountered anomalies that challenged explanations within the framework of Big Bang theory. Most notably, the absence of predicted relics, such as magnetic monopoles or particles from grand unification, has led many to reconsider aspects of the theory. The universe we observe today appears to require forces beyond our current understanding. However, these forces remain elusive. At its origin, the The universe required a precise rate of expansion to balance the overall energy density, something the standard model of cosmology struggles to account for. This led to neither perfect equilibrium nor sufficient time for energy exchange across different regions of space. Given the vastness of the universe and its expansion over time, these anomalies pose significant challenges to cosmology and the scientific community as a whole. The inflationary model and its challenges. While existing theories fail to account for observed anomalies, two approaches emerge: refine current theories or consider alternative explanations. The theory of inflation has emerged as the most promising framework for extending the Big Bang perspective. Inflation proposes a brief period of rapid expansion that smooths the universe, bestowing uniform properties. It addresses the horizon problem and predicts the development of quantum fluctuations, which manifest as density and temperature variations. The predictions of inflation align with observed patterns and fluctuations, supporting its validity. Although alternative theories exist, inflation's scientific strength remains unparalleled. Nonetheless, despite past contributions to general relativity and singularities, Roger Penrose's work, along with his collaboration with Stephen Hawking, failed to match the development of inflation in explaining the earliest moments of the universe. Recently, there has been deliberate work to undermine the validity of inflation theory, advocating for conformal cyclic cosmology. However, this theory is inherently flawed from a scientific perspective. The key distinction lies in their predictions. Conformal cyclic cosmology proposes that remnants from a universe preceding the Big Bang are imprinted in the cosmic microwave background and the large-scale structure of a universe. On the other hand, inflationary theory maintains that the end of inflation and the hot Big Bang are causally disconnected from any pre-Big Bang era. James Webb Telescope's astonishing discoveries. Space scientists quickly recognized anomalies in the images sent by the James Webb Space Telescope since 2022. These discoveries may necessitate a reassessment of key aspects of the universe's origins and evolution. One significant discovery made by the Webb telescope was the presence of fully formed galaxies much earlier than expected by the standard cosmological model. This anomaly challenges the established sequence of events following the Big Bang, where stars and black holes form first, followed by galaxies. Such discoveries disrupt our understanding, much like encountering grandparents portrayed as children in a story. Moreover, recent evidence has uncovered irregularities within the major theories of the universe, such as the persistent error in determining the Hubble constant, which continues despite improvements in data accuracy and collection methods. New data from Webb exacerbates existing challenges to the current cosmological model. These issues highlight imperfections within the model, raising questions among scientists and physicists. While the model has undergone changes in recent years to align with emerging data, some argue that these adjustments have been too accommodating. As a result, there is growing recognition that a shift in cosmological understanding may be necessary. Perspective may be necessary, possibly reshaping our understanding of the universe's fundamental properties. The standard model of cosmology, hailed as a triumph of human knowledge, emerged from Edwin Hubble's groundbreaking discovery of the expanding universe in the 1920s. Subsequent discoveries, such as the detection of the cosmic microwave background radiation in 1964, confirmed the Big Bang theory as the most viable explanation for the universe's origins, depicting the early universe as a hot, dense soup of subatomic particles gradually cooling over time. Reconsidering cosmology in light of new evidence. Achieving the current level of precision in cosmological understanding has required theoretical extrapolation beyond observational data. The idea of infinite expansion, introduced in 1981, was brought in to resolve inconsistencies in earlier Big Bang models, further emphasizing the dynamic nature of cosmological theory. According to this model, the early universe underwent rapid, unprecedented expansion shortly after the Big Bang. While certain issues are resolved by this theory, new challenges arise, particularly in light of the prevailing belief in the existence of a single universe. Perhaps there are countless others beyond our observational reach. Some detectable anomalies, such as hypersingularities within black holes, find support through indirect evidence. However, the shocking discoveries of the Webb Space Telescope regarding the formation of galaxies, along with ongoing issues with the Hubble constant, raise concerns that we may be approaching a tipping point where a significant overhaul of our current cosmological model becomes essential. This could require a complete reassessment of the fundamental building blocks of the universe, including the very nature of existence itself. Cosmology, unlike many other scientific fields, deals with fundamental questions about the universe, its origins, and our role within it. The study of consciousness and quantum physics also explores similar themes, examining the intersection of theory and reality. It is crucial to scrutinize these foundational assumptions, given the impact of theoretical presuppositions on data collection. History has shown that shifts in scientific thought, such as the transition from geocentrism to heliocentrism or the discoveries of evolution and relativity, have led to profound changes in societal perspectives. A similar transformation in our understanding of the universe may be imminent as a result of any forthcoming scientific revolution in cosmology. Philosopher Robert Anton Wilson argues that theory becomes crucial when further scientific inquiry fails to provide satisfactory answers to a question. Ongoing debates among established scientists about climate theory suggest that cosmological essentials might, in fact, need to be addressed. If revising existing models proves insufficient, a complete upgrade of our understanding of the universe might soon become necessary. The role of the James Webb Space Telescope. Recent advances in observational technology have transformed our understanding of the universe. The James Webb Space Telescope, with its cutting-edge instruments, allows cosmologists to peer further back in time than ever before, capturing light from the early universe that has traveled billions of years to reach us. This capability has changed our perspective on cosmic history, revealing patterns and anomalies that challenge long-held beliefs. One of the most significant implications of Webb's discoveries is the potential to re-evaluate the timeline of cosmic development. For example, the discovery of mature galaxies just a few 100 million years after the Big Bang raises questions about the speed and nature of galaxy formation. This observation suggests that the processes governing star and galaxy development might have been more complex and efficient than previously understood. The consequences of these findings challenge assumptions about the ongoing evolution of cosmic structures and suggest that large-scale star formation may have occurred much earlier than current models predict. Additionally, the discovery of unusual patterns in the cosmic microwave background radiation, combined with data from Webb, suggests that our universe may be more homogeneous and isotropic than the Big Bang model can fully explain. This has sparked discussions about the plausibility of a multiverse, where our universe is just one of many, each with its own unique properties. Such a perspective would not only reshape our understanding of physical laws but also expand the boundaries of scientific inquiry. While we may not be able to directly observe other universes, astronomers continue to analyze data from Webb. The potential for discovering exoplanets and habitable zones around distant stars has reignited interest in astrobiology. The study of conditions on these exoplanets could provide insights into the chemical signatures of life beyond Earth. This search could ultimately lead to significant philosophical questions about our place in the universe and whether we are alone in the vastness of space. Moreover, recent findings from Webb have prompted a reassessment of dark matter and dark energy, two of the universe's most mysterious components. The anomalies observed in galaxy rotation curves and the distribution of large-scale structures may point to new particles or forces that deviate from existing theoretical models. The James Webb Space Telescope continues to provide groundbreaking data, offering a wealth of new insights that challenge traditional models of cosmology. One of the most notable discoveries is the presence of unexpected large-scale structures that seem to have formed much earlier in the universe's history than current models suggest. This raises intriguing questions about the mechanisms of cosmic evolution. For example, the discovery of galaxies with well-defined features and mature stars only a few 100 million years after the Big Bang points to the possibility that processes like galaxy mergers, star formation, and black hole accretion could have occurred much more rapidly than previously thought. This new evidence has profound implications for our understanding of cosmic history. If galaxies were able to form so quickly, it suggests that the conditions necessary for galaxy formation could have been more favorable or widespread than earlier models assumed. This discovery forces scientists to reconsider not only the timeline of galaxy formation, but also the underlying conditions that allowed for such rapid development. The presence of complex structures at such an early stage of the universe also implies that the laws of physics, at least as we understand them, may have behaved differently in the early universe than they do today. Additionally, the Webb telescope's observations are enhancing our understanding of the role of dark matter and dark energy, two enigmatic components that make up most of the universe's mass-energy content. The peculiar behavior of galaxies observed by Webb could offer clues to the nature of these mysterious forces, suggesting that they may be interacting in ways that current theories fail to account for. For example, the distribution of dark matter in galaxy clusters may not be as uniform as previously thought, and some unusual gravitational lensing effects could point to new physics beyond the standard model. As scientists continue to analyze the data, They are also exploring the possibility of multiverse theories, which have gained traction in recent years. Webb's discoveries could provide the observational evidence needed to support these ideas, which propose that our universe might be just one of many, each with its own unique set of physical laws. The possibility of parallel universes challenges everything we know about space, time, and reality, raising profound philosophical questions about the nature of existence itself.